Welcome to qnawire.
Okay, so we have two masses on a string problem, but the gimmick of this problem is that the string itself has mass, so that will complicate things a little bit. So this is a vertical type of problem, so we have a mass up here, and then I'm going to draw the rope like that, and then a second mass down here. So we are drawing free body diagrams for all of these bodies, and I find it easiest to definitely not start in the middle, but either start at the top or the bottom. Let's start from the bottom because gravity acts downward. So I'm going to call this blocks or item C in this problem. It's going to have a gravitational force directed downward, and then I'm going to call this a second tension force, T2, that's acting upward because it's being pulled along by a rope. And then working our way upward, we know that there must be a Newton's third law reaction pair. So that's tension 2, also pointing downward. Force of gravity is also involved, so it's mvg. And then a potentially different tension force, T1, acting upward. And similarly, in block A, we have the tension force also acting downward, gravity acting downward, and then an applied force acting upward. So let's call that F. Okay. Additionally, the problem wants us to explicitly state for all the forces what body is exerting that force. So I would say the easiest one to do first is all the gravities, and Earth is exerting the gravitational force on all three of those. On the tension forces, it's just coming from the adjacent or neighboring bodies. So for T2 on item 3, that would be B, and vice versa. And then for T1, it's coming from A, and then up here, it's coming from B. And then honestly, based on the grammar of the problem, they don't tell us what's causing the external applied force. So you can put yourself, maybe you're holding it by a string, but I'm just going to put a question mark there because it's ambiguous as to what it is. In part B, we want to find what the acceleration of the system is. So we'll go ahead and do that by turning our three free body diagrams into three equations of motion using Newton's second law. So we have F is equal to ma for block 1. So the sum of the forces is F minus T1 minus mag, and do similar things for blocks B and C. And note that the accelerations are all the same because they're connected by a string, so they all need to be moving and therefore accelerating together. T2 minus mcg. Okay, and I think the easiest way to solve for acceleration is just add these three equations together. So on the left-hand side, if I collect terms, I get the total mass multiplied by their joint acceleration. And then we see that the tensions all cancel out if I add them on this side. So I'm just left with the applied force minus, again, the sum of the masses and multiplied by gravity. Okay, so now I can solve for acceleration by dividing both sides by total mass. Minus g, and then we plug in numbers. Let's do that down here, actually. So we have 6 plus 4 plus 5. And then the applied force is 200 newtons. And then subtract off that gravity, 9.81. Plug that into a calculator, and then you get an acceleration of 3.52 meters per square second. Good. And I think we can fit part C up here. Let's draw some boundaries. Okay, so in part C, we now want to find what the tension on the top of the rope is. So that is T1. And then we can get T1 by, I think the easiest way to do it is to rearrange our first equation, Newton's second law applied to block A, because we now know what the acceleration is. So rearrange terms in order to solve, or rather isolate tension and solve for it. So that's minus MAG minus MAA. Plug in numbers. We know F is 200. We know the mass is 6. And I'm just going to collect some terms and do 9.81 plus 3.52 for the acceleration. And then get a tension force of 120 newtons at the top of the rope specifically. Okay, and then in part D, I think the easiest way to visualize this is to break up the rope into two parts because we want to know what the tension at the bottom of the rope is. So in other words, I'm going to break the rope into two parts like so, and extend our free body diagram. So we have T1 still pointing upward, and then MB over 2G is the gravity acting on this rope, and then T mid is the tension at halfway through the rope. So T mid is also going to be applied to the top of the bottom half of the rope. It also has a weight of MB over 2G because we split it in half, and then T2 is acting downward on that half. Okay, so let's draw a free body diagram, or sorry, let's apply Newton's second law to the top half of the rope. And again, we're trying to solve for T mid. So MB over 2A is going to be equal to T1 minus MB over 2G minus T mid. So now we can isolate T mid as T1 minus MB over 2A plus G. Plug in numbers. MB is 5. No, it's 4, sorry. 2. Acceleration we already found was 3.52. Gravity we also already found, 9.81. Plug in numbers and then get that T mid to 3 significant figures is 93.3 newtons. Sorry, 93.3 newtons.